I want you to do something for me. Tonight, when it gets dark, when the sun has finally gone and the sky has turned from purple to black, go outside. Go somewhere away from the city if you can. Away from the street lights, away from the glow of shopping centers and motorways and the 10,000 electric sources that have made our nights permanently, artificially bright. Find a field. Find a hilltop. Find somewhere genuinely dark. And look up. On a clear night, far from any city, you can see approximately 5,000 individual stars with the naked eye. 5,000 points of ancient light scattered across the dome of the sky like salt thrown across black velvet. They appear to be scattered randomly, but they are not. They have structure. They are part of a vast architecture we can only fully appreciate from outside it. What you are looking at is a small, utterly insignificant slice of the Milky Way galaxy. Our galaxy contains, by the best current estimates, between 200 and 400 billion stars. Not millions, billions. 400 billion suns, most of them older than ours, most of them warmer or cooler or larger or smaller in ways that might make them better or worse at nurturing life on any worlds they host. And the Milky Way, our galaxy, the only galactic home humanity has ever known, is itself just one of an estimated 2 trillion galaxies in the observable universe. 2 trillion, a number so large that if you spent 1 second looking at each galaxy, it would take you 63,000 times longer than the current age of the universe to finish. The scale is not merely large, it is incomprehensible. It breaks the machinery of human intuition completely. Now, hold all of that in your mind. The 400 billion stars in our galaxy alone, the 2 trillion galaxies beyond, the age of it all, 13.8 billion years since the Big Bang, during which stars have formed and died and formed again in cycles, scattering the heavy elements needed for rocky planets and carbon-based chemistry across every corner of the cosmos. Astronomers now know with a certainty that was unthinkable 30 years ago that planets are not rare. They are the default outcome of star formation. Most stars have them. And among those planets, a substantial fraction sit at distances from their stars where liquid water can exist on a surface, the basic requirement, as far as we understand it, for life as we know it. Conservative estimates place the number of potentially habitable worlds in the Milky Way at 300 million. Some estimates run into the billions. These are not science fiction numbers. They come from the data of the Kepler Space Telescope, from the analysis of thousands of confirmed exoplanets, from the hard mathematical output of peer-reviewed planetary science. So, here is the arithmetic. Hundreds of billions of stars, hundreds of millions of potentially habitable worlds, 13.8 billion years of time for chemistry to become biology, for biology to become complexity, for complexity to become intelligence, for intelligence to become technology, for technology to reach across the stars. If even 1 in a million habitable worlds ever produces a technological civilization, a number so conservative that it borders on pessimism, our galaxy should currently contain hundreds of advanced species. And if even one of those species arose a billion years before us and developed interstellar travel, the mathematics of colonization wave propagation tells us clearly and unambiguously that the entire Milky Way could have been settled, explored, and transformed long before our sun even ignited from its birth nebula. So, I ask you a question, the simplest, most devastating question in the history of science. Where is everybody? In the summer of 1950, one of the greatest physicists of the 20th century sat down to lunch at Los Alamos National Laboratory in New Mexico with 3 colleagues. The conversation was light. They were talking about a recent New Yorker cartoon, a joke about flying saucers. They were laughing. And then the physicist went quiet. You could see him calculating, running numbers in his head with that extraordinary facility he had,
the gift for reducing any problem to its essential mathematics that had made him a legend in physics before he was 40. A few minutes later, he looked up from whatever inner calculation he had been performing and asked a question so simple that his colleagues later said they understood its full implications only gradually over the days and years that followed. His name was Enrico Fermi, and the question was, but where is everybody? The Fermi Paradox was born at a cafeteria table over lunch in the summer of 1950. And in the 75 years since that afternoon, we have pointed the most powerful radio telescopes ever built at the sky and listened. We have searched hundreds of thousands of stars across a broad spectrum of frequencies. We have looked for the infrared signatures of megastructures that advanced civilizations would inevitably build. We have scanned for laser pulses, for gamma-ray patterns, for anomalous gravitational signatures, for any deviation from the expected background of natural astrophysical processes that might indicate the presence of something deliberate, something constructed, something minded. We have found nothing. Not a signal, not a probe, not an artifact, not a whisper, not a shadow. Nothing. The universe, which by every calculation should be overflowing with intelligence, presents to our instruments an unbroken, perfect, haunting silence. Today, we journey through the evidence that makes this silence so strange, through the theories that attempt to explain it, and through the implications, some of them deeply unsettling, about the nature of intelligence itself, about what happens to civilizations like ours, and about our own future in this vast, quiet cosmos. Prepare yourselves. We begin.
To understand the full weight of what Fermi asked that summer afternoon, you need to understand who Enrico Fermi was, because the question derives much of its power from the person asking it. This was not an idle speculation from a dreamer or a science fiction enthusiast. This was a calculation from one of the most rigorous, most precise scientific minds of the 20th century. Fermi was born in Rome in 1901. By his mid-20s, he was already rewriting the textbooks of quantum mechanics. By his 30s, he had won the Nobel Prize in Physics, awarded in 1938 for his work on nuclear reactions induced by slow neutrons, work that directly enabled the development of nuclear reactors and ultimately nuclear weapons. When he accepted the prize in Stockholm, he did not return to fascist Italy. He sailed instead to New York and began what would become one of the most consequential scientific careers ever conducted on American soil. In December 1942, beneath the stands of a disused squash court at the University of Chicago, Fermi oversaw the construction and activation of Chicago Pile 1, the world's first artificial nuclear reactor. He achieved the first controlled self-sustaining nuclear chain reaction on December 2nd of that year. He was among the key scientific architects of the Manhattan Project. He witnessed the Trinity nuclear test in July 1945. By 1950, when he sat down to that lunch at Los Alamos, Fermi had spent years living with the implications of what human ingenuity could produce. He had seen science transform from an abstract enterprise of discovery into a force capable of reshaping civilization, capable, for the first time in history, of ending it. This context matters, because when Fermi asked, "Where is everybody?" he was not asking it naively. He was not unaware of the physics of interstellar travel, or of the age of the universe, or of the statistical arguments that should fill the galaxy with minds. He was a physicist who had spent his career making seemingly impossible things happen through the application of relentless mathematical rigor to the physical world. And what he was really asking, beneath the simple phrasing, was this: the universe is old enough, large enough, and apparently hospitable enough that we should not be alone. And yet, by every measure available to us, we are alone. What does this contradiction tell us? His colleagues at that lunch, Emil Konopilsky, Edward Teller, and Herbert York later recalled that the question arrived almost as a joke. They laughed, but then they thought about it, and Fermi, being Fermi, immediately began working through the numbers. He estimated right there at lunch how long it would take an interstellar-capable civilization to colonize the galaxy. His conclusion was that it shouldn't take very long at all, certainly not longer than a small fraction of the galaxy's age, and the galaxy is very, very old. The question dissipated over the rest of the meal, as lunch conversations do. Fermi died of cancer 4 years later, in November 1954, at the age of 53. He never published anything formal on the topic. The paradox that bears his name was reconstructed from the recollections of the men who were there that day. But the question itself proved impossible to let go of. It had the quality of the best scientific questions, simple enough to state in a single sentence and deep enough to occupy generations of brilliant minds without resolution.
To truly feel the weight of the silence, you need to walk through the argument for why the galaxy should be loud. You need to understand, step by step, why the expectation of contact is not wishful thinking, but a sober mathematical conclusion. Let us begin with time. The Milky Way is approximately 13.6 billion years old. Our Sun, a relatively young star by galactic standards, ignited roughly 4.6 billion years ago. This means that for the 9 billion years before our Sun even existed, the galaxy was already producing stars, scattering heavy elements through supernova explosions, and creating the conditions for rocky planets to form around second and third generation stars. 9 billion years is an almost incomprehensibly long runway. In the roughly 4 billion years since life first appeared on Earth, evolution produced bacteria, then complex cells, then multicellular organisms, then animals, then mammals, then primates, then us. And we, in the last few thousand years, the last blink of geological time, have gone from stone tools to radio telescopes. The entire arc of human technological development fits into an interval of time so short that on the scale of the galaxy's history, it is essentially instantaneous. Now imagine a civilization that had 4 billion years of evolutionary head start, or 6 billion, or 9 billion. What would they look like? What would they be capable of? Our own technological trajectory suggests that the gap between us and a civilization a million years more advanced would be so vast as to be essentially incomprehensible, and a million years is nothing on the timescale of the galaxy. A civilization a billion years more advanced than us would be to us as we are to the single-celled organisms that dominated Earth for the first 2 billion years of its history. These are not small numbers. They are not speculative. They are just time. And time is what makes the silence strange. Now let us add space. The Milky Way is approximately 100,000 light-years across. That is the distance light travels in 100,000 years, and light moves at 300,000 kilometers per second. It is genuinely vast by any human standard, but consider, a civilization capable of sending spacecraft at 1% of the speed of light, not an implausible capability for a species a few thousand years more advanced than us, and we ourselves may achieve it within centuries, could traverse the galaxy in 10 million years. 10 million years, which sounds long until you remember the galaxy is 13,600 million years old. 10 million years is less than 1/10 of 1% of the galaxy's age. On the cosmic clock, it is nothing, a rounding error, a moment. In 1975, physicist Michael Hart at the National Center for Atmospheric Research in Colorado published a rigorous analysis of this problem in a paper titled simply Explanation for the Absence of Extraterrestrials on Earth.
Hart worked through every conceivable reason why a galaxy-spanning civilization might not have reached us. The distances were too great, the motivation to travel was insufficient, civilizations chose not to colonize, civilizations destroyed themselves before they could spread. He examined each hypothesis with mathematical rigor and found each one wanting. His conclusion was stark, and it has never been fully refuted. Hart argued that the most parsimonious explanation for the absence of extraterrestrials on Earth, the simplest explanation consistent with all available evidence, is that there are no other technological civilizations in our galaxy. Not that they are hiding, not that they are not interested, not that we haven't looked hard enough, simply that they do not exist. It was a paper that the scientific community found deeply uncomfortable, and 5 years later, physicist Frank Tipler at Tulane University made the argument even sharper. Tipler drew on the theoretical work of mathematician John von Neumann, who in the 1940s had laid the mathematical groundwork for machines capable of self-replication, machines that could construct copies of themselves from available raw materials. Von Neumann probes, as they came to be called, are a theoretical class of spacecraft that could be launched toward a nearby star system, arrive after a journey of decades or centuries, use the local materials to build copies of themselves, and send those copies on to further star systems. The generation of probes would seed multiple new systems. The colonization wave would expand exponentially. Tipler calculated that a single von Neumann probe, launched once from a single star system, could colonize the entire Milky Way within a few tens of millions of years, even traveling at a small fraction of the speed of light. The galaxy should be saturated with such probes. Our own solar system should be full of them. We should have found them by now. We have not. The absence of von Neumann probes in our solar system is itself a data point of enormous significance. It does not merely suggest that no one is broadcasting signals. It suggests that no one, in the entire 13 billion-year history of the galaxy, has ever launched a self-replicating exploration program. Either that, or something stops them before they can. But before we descend into the explanations, some of which are far darker than others, we need to understand exactly how hard humanity has actually tried to hear something. Because an easy dismissal of the paradox is to say, we haven't really looked, the universe is enormous, of course we found nothing yet. That dismissal, as we are about to discover, is not quite as reassuring as it sounds.
In October 1961, 11 years after Fermi's lunch and 7 years after his death, a young astronomer named Frank Drake convened the world's first serious scientific conference on the search for extraterrestrial intelligence. The venue was the National Radio Observatory at Greenbank, West Virginia, a facility nestled in a rural valley specifically chosen because the surrounding mountains shield it from radio interference. The attendees included some of the most distinguished scientists in America, among them the young Carl Sagan, the dolphin communication researcher John Lilly, the Nobel laureate Melvin Calvin, and Otto Struve, one of the foremost stellar astronomers of his generation. Drake wanted to structure the discussion. He needed a framework, a way to organize the vast unknowns into something manageable. The night before the conference, he sat down and wrote what became the most famous equation in astrobiology. The Drake equation is not a formula that produces a precise answer. It is better understood as a way of mapping our ignorance, a method for identifying exactly which questions we need to answer before we can make any confident estimate of the prevalence of technological intelligence in the galaxy. It expresses the number of currently communicating civilizations in the Milky Way as a product of several factors multiplied together. Those factors are the rate at which new stars form in the galaxy, the fraction of those stars that have planetary systems, the average number of planets per system that could support life,
the fraction of those planets where life actually arises, the fraction of life-bearing worlds where intelligence develops, the fraction of intelligent species that develop detectable technology, and finally, the average lifespan of a technological civilization, the length of time it remains in a communicating state. Multiply all of these together and you get n, the number of civilizations we might expect to be able to contact right now. Here is what makes the equation so instructive and so unsettling. The first three terms are astronomical, and we now know them quite well. The Milky Way forms roughly 3 new stars per year. Thanks to the Kepler Space Telescope, which we will discuss in detail shortly, we know that the vast majority of stars have planets, with the occurrence rates for Earth-sized planets in habitable zones around Sun-like stars falling somewhere between 20 and 50%. These numbers are robust. They come from direct observation of thousands of planetary systems. Drake's 1961 guesses for these terms turn out to have been, remarkably, quite close to the mark. It is the biological and sociological terms where our uncertainty explodes. What fraction of habitable planets actually produce life? We have exactly one data point in our entire history of observation: Earth. We know life arose here. We know it arose relatively quickly. The earliest evidence of microbial life on Earth dates to roughly 3.7 billion years ago, only a few 100 million years after the planet cooled enough to support liquid water. Whether this means life arises readily wherever conditions allow, or whether Earth was extraordinarily lucky, we simply cannot say. Our sample size is 1. What fraction of life-bearing worlds produce intelligence? Again, one data point. Intelligence, the kind that asks questions about the universe and builds tools to answer them, arose on Earth. But it arose only once in 4 billion years of biological evolution on a planet that has hosted millions of distinct species. Dinosaurs dominated Earth for 160 million years and left no lasting technological civilization. Intelligence is not the inevitable outcome of evolution. It may be, in the language of evolutionary biology, a highly contingent outcome, something that required a specific and unlikely sequence of circumstances. And then there is the final term, which many researchers now consider the most important and the most frightening: the average lifespan of a technological civilization, the length of time it remains in a communicating state. Drake's equation makes no prediction of which of these scenarios is true. It simply shows us that the question of civilizational longevity is central to everything. And the evidence forces us to confront an uncomfortable possibility. The answer may be visible in the silence itself.
The optimism that surrounded Drake's equation in its early years was genuine and remarkable. In 1966, Carl Sagan and the Soviet astrophysicist Iosif Shklovsky published a landmark book titled Intelligent Life in the Universe, which argued that the galaxy likely teemed with advanced civilizations, some of them millions or billions of years more developed than us. The book was not fringe speculation. Sagan was one of the most rigorous and respected scientists of his generation. He and Shklovsky estimated that perhaps 1 million technological civilizations existed in the Milky Way right now. 1 million civilizations, the nearest of them potentially only a few hundred light-years away, detectable perhaps with radio telescopes we could already build. First contact, many believed, was a matter of decades away at most. Drake himself had begun the search the previous year. In 1960, he pointed the 26-meter radio telescope at Green Bank toward 2 nearby Sun-like stars, Tau Ceti and Epsilon Eridani, both within 12 light-years of Earth, and listened for artificial radio signals. He chose a frequency of 1420 megahertz, the emission frequency of neutral hydrogen, the most abundant element in the universe, on the principle that any sufficiently advanced civilization with radio astronomy capability would know about this frequency and might consider it a natural beacon, a cosmic lingua franca. He called the project Ozma, after the queen of the fictional land of Oz, something distant, fabulous, and possibly impossible to reach. He heard nothing from either star. But the field was young. The technology was primitive by later standards. The search had barely begun. The scientific consensus in 1960 was that finding a signal was merely a matter of time and of pointing the right telescope in the right direction. It was in this atmosphere of optimism that Soviet astrophysicist Nikolai Kardashev proposed in 1964 a framework that would permanently reshape how scientists thought about advanced civilizations. Kardashev was interested in a practical problem. If an alien civilization were transmitting a signal, how powerful would that signal be, and how powerful could it be, given the physical constraints of the cosmos? To answer this, he proposed a classification system based on energy use, what became known as the Kardashev scale. A Type 1 civilization harnesses all the energy available on its home planet, something humanity has not yet fully achieved. We are currently estimated to be at roughly Type 0.73, using only a fraction of the energy our planet receives from the Sun. A Type 1 civilization controls weather, manages geological processes, and uses the full energy budget of its world. A Type 2 civilization has expanded beyond its home planet to harness the total energy output of its star, approximately 3.8 times 10 to the power of 26 watts. This is the civilization that builds a Dyson sphere, or some equivalent megastructure. It commands energies roughly 10 billion times greater than anything humanity currently produces. A Type 3 civilization has colonized its galaxy and harnesses the total energy output of all its stars, a power roughly 10 billion times again greater than a Type 2. This is the civilization that reshapes galaxies, that is visible across intergalactic distances, that leaves marks on the large-scale structure of the cosmos. Kardashev's framework was not just a classification scheme, it was a statement about what SETI should be looking for. A Type 3 civilization would be unmistakable. It would transform the observable properties of an entire galaxy. A Type 2 civilization would produce detectable infrared signatures, as we have discussed. Even a Type 1 civilization, communicating with the full power of its planet's energy budget, could produce signals detectable across thousands of light years with radio telescopes. The reason this matters is that the Kardashev scale, combined with the age of the galaxy, produces an expectation that should alarm us. Even if Type 2 and Type 3 civilizations are rare, the galaxy has been producing stars and planets for 13 billion years. If even one civilization per billion years per galaxy achieves Type 3 status, the Milky Way should currently host at least 13 of them. And a Type 3 civilization cannot be hidden. It restructures everything around it. We see no such restructuring anywhere. More than 60 years later, we are still waiting, and the silence, which once seemed like simple evidence of insufficient search effort, has begun to feel like something more than that.
Before we can assess what the silence means, we need to be precise about something that is often misunderstood. Exactly how extensively has humanity searched? Because the most common response to the Fermi Paradox from people encountering it for the first time is a reasonable-sounding dismissal. The galaxy is enormous, they say. We've only been listening for a few decades. Of course we haven't found anything yet. It's like searching one grain of sand on a beach and concluding there is no water nearby. This analogy is appealing. It is also, on closer examination, not quite right. Let us look carefully at what we have actually done. The first modern SETI survey, Drake's Project Ozma, was conducted in 1960 with the 26-meter Green Bank telescope, targeting 2 stars over a period of a few months. It was, by subsequent standards, extraordinarily limited.
But what followed was decades of increasingly sophisticated, increasingly comprehensive searches that together represent a genuinely substantial observational effort. Through the 1970s and 1980s, the Big Ear Radio Telescope at Ohio State University conducted a continuous SETI survey of the sky, scanning frequencies, sweeping celestial coordinates, accumulating data year after year. It ran for 22 years until the telescope was demolished in 1998 to make way for a golf course extension, a fact that still causes considerable bitterness in the SETI community. During its operation, it produced the only candidate signal in the history of SETI that has never been satisfactorily explained, the WOW signal of 1977, which we will examine in detail shortly. In the 1990s and 2000s, the SETI Institute in Mountain View, California, became the primary home of organized searches. Founded in 1984 with Carl Sagan on its board of trustees, the Institute developed the Phoenix Project, the most comprehensive targeted search of nearby stars conducted to that point, examining approximately 800 Sun-like stars within 200 light-years of Earth across a broad range of microwave frequencies. It found nothing. Then came Breakthrough Listen. In July 2015, Russian billionaire and science philanthropist Yuri Milner announced the largest single investment in SETI in history, $100 million over 10 years, dedicated to the most comprehensive search for extraterrestrial intelligence ever conducted. The program, called Breakthrough Listen, was structured by Milner in collaboration with Stephen Hawking, Frank Drake, Anne Druin, Carl Sagan's widow and scientific partner, and the astronomer Martin Rees, the Astronomer Royal of the United Kingdom. Breakthrough Listen secured access to two of the world's most powerful radio telescopes, the Green Bank Telescope in West Virginia, a fully steerable 100-meter dish capable of extraordinary sensitivity, and the Parkes Observatory in New South Wales, Australia, giving the program coverage of the entire sky. It also incorporated the Automated Planet Finder optical telescope at Lick Observatory in California, searching for artificial laser signals. Between 2016 and the mid-2020s, Breakthrough Listen has surveyed over 1 million individual stars across the full range of radio frequencies most likely to carry artificial signals. It has scanned the centers of 100 nearby galaxies. It has generated more data about the radio sky than all previous SETI programs combined. Every single one of the over 1 million stars surveyed has yielded nothing. But radio is not the only modality we have searched. In 2015, astronomer Jason Wright at Penn State University and his collaborators conducted a comprehensive infrared survey of the galaxy using data from NASA's WISE telescope, the Wide Field Infrared Survey Explorer, specifically looking for the waste heat signatures that a Kardashev Type 2 or Type 3 civilization would necessarily produce. The logic is simple. A civilization that has harnessed the total energy output of a star, constructing what the physicist Freeman Dyson in 1960 called a Dyson sphere, would radiate that energy as infrared heat, producing a characteristic spectral signature detectable across vast distances. Wright's team searched 100,000 galaxies for anomalous infrared signatures consistent with civilization-scale energy use. They found about 50 galaxies worth investigating more closely. Every single one turned out to have a natural explanation, typically dust heated by star formation or the energetic output of active galactic nuclei, or both. Not one showed evidence of engineering. In parallel, the Harvard SETI group, led by Avi Loeb, and later the Panoramic SETI program developed by researchers at UC Berkeley, began searching for nanosecond optical laser pulses, the kind of signal that an advanced civilization might use for tight-beam interstellar communication. Optical SETI has the advantage of being able to transmit enormously more information per unit of power than radio, and any civilization with laser technology, something we ourselves achieved in 1960, might prefer it. Silence there too. And then there is the search our instruments did not design, but which the universe conducted for us, the search written into the geological and astronomical record of our own solar system. If von Neumann probes exist and have been traversing the galaxy for millions of years, some of them should have reached and explored our solar system long ago. We have now sent spacecraft to every planet in the solar system, landed on several moons, and surveyed the asteroid belt and the Kuiper belt with sufficient resolution to say with confidence that there are no large artificial structures in the inner solar system. The Galileo project, launched in 2021 by Avi Loeb at Harvard University, is currently conducting a systematic survey of near-Earth space for anomalous objects, including the monitoring of potential interstellar visitors to our solar system, following the 2017 passage of the object known as Oumuamua through our solar system. We will return to Oumuamua later. But the summary, after more than 60 decades of increasingly sophisticated searching, is unambiguous. We have looked hard and with growing sophistication at a very large piece of the galaxy, and we have found absolutely nothing that cannot be explained by natural astrophysical processes. This represents just one piece of a much larger puzzle, but it is an important piece. The silence is not the product of insufficient effort. The silence is real.
While SETI was listening and hearing nothing, a parallel revolution was transforming our understanding of the raw ingredients available for life in the cosmos. And that revolution made the silence stranger than ever before. For most of human history, we had no idea whether other stars hosted planets. We knew our sun had them. We could see 5 of them with the naked eye on any clear night, wandering against the fixed background of stars. But whether stars in general were accompanied by planetary systems, or whether our sun was unusual in this regard, was entirely unknown. The first confirmed detection of a planet orbiting another star did not come until 1992, when astronomers Alexander Wolszczyn and Dale Frail detected 2 planets orbiting a pulsar, a dead neutron star, using the Arecibo telescope in Puerto Rico. The first confirmed detection of a planet orbiting a normal Sun-like star followed in 1995, when Michel Mayor and Didier Queloz at the Geneva Observatory discovered a gas giant orbiting the star 51 Pegasi using the radial velocity method, measuring the tiny wobble the planet's gravity induces in its host star. Mayor and Queloz won the Nobel Prize in Physics for this discovery in 2019. But the true revolution came from space. The Kepler Space Telescope was launched by NASA on March 6, 2009, into an Earth-trailing solar orbit. Its mission was elegantly simple: stare at a single patch of sky containing approximately 150,000 stars for 4 continuous years, measuring the brightness of each star with extraordinary precision, and look for the tiny, regular dips in brightness that occur when a planet transits between its star and our line of sight. The data Kepler returned transformed our understanding of planetary demographics permanently. Over its primary mission and extended K2 mission, Kepler confirmed 2,662 exoplanets and identified several thousand more candidates awaiting confirmation. But the most important output was not the list of individual planets. It was the statistical picture the data painted of planetary occurrence rates around different types of stars. The conclusion was stunning. Planets are not a rarity associated with particular types of stars under particular circumstances. They are the default outcome of star formation. They emerge naturally from the protoplanetary disk of gas and dust that surrounds virtually every young star as it forms. The question is not whether a star has planets. The question is what kind. Kepler found that approximately 70% of Sun-like stars host at least one planet. It found that Earth-sized planets are common, far more common than gas giants like Jupiter, which were initially overrepresented in the exoplanet catalogs because of observational biases. And it found that a substantial fraction of stars, estimates ranging from 11 to 41% depending on methodology, host at least one Earth-sized planet in what scientists call the habitable zone, the range of orbital distances where the planet's surface temperature could permit liquid water to exist. In 2020, a team led by Steve Bryson at NASA's Ames Research Center published a comprehensive analysis of Kepler data combined with spectroscopic characterization of host stars, producing the most careful estimate yet of the frequency of habitable zone Earth-sized planets around Sun-like stars. Their result? Approximately 1 in 4 such stars may host a habitable world. With roughly 4 billion Sun-like stars in our galaxy, in just this one stellar category, excluding the far more numerous red dwarf stars, which have their own habitable zones and their own controversies regarding habitability. The TESS mission, the Transiting Exoplanet Survey satellite, launched in 2018 as Kepler's successor, is conducting an all-sky survey of nearby bright stars, identifying the closest and most easily studied exoplanets. Among its discoveries are worlds close enough to Earth that the James Webb Space Telescope can directly analyze their atmospheres for the chemical signatures of life. We will return to what Webb has found and has not found shortly. But first, consider the full picture Kepler and its successors have painted. A galaxy with 400 billion stars, most of them with planets, hundreds of millions of those planets in the right temperature range for liquid water. The chemical building blocks of life, amino acids, nucleotides, organic compounds, detected in interstellar gas clouds, in cometary material, in meteorites from the asteroid belt. The very building blocks of DNA and proteins, pre-assembled by the chemistry of the cosmos itself, raining down on planets throughout the galaxy. The universe is not merely permitting life, it is, by every indication, attempting to build it everywhere. And yet, the sky is silent. The more we learn about how common the raw materials of life are, the more extraordinary the silence becomes. It is not the silence of a barren universe, it is the silence of a universe that should be full, and somehow isn't. At least, not in any way we can detect.
On the evening of August 15, 1977, the Big Ear radio telescope at Ohio State University was doing what it always did, sweeping the sky, recording data on a bank of computer printouts, looking for anomalies in the background radio noise of the cosmos. The telescope was not staffed continuously. Researchers would come in, collect the printouts, and analyze them later. A few days after that August evening, a volunteer researcher named Jerry Emmon, a former Ohio State professor who had worked with the Big Ear program since its founding, sat down with a stack of printouts and began the routine work of scanning the columns of numbers for anything unusual. What he found was not routine. In the midst of the background noise, the standard alphanumeric codes that represented weak radio signals of known natural or terrestrial origin, a sequence of characters leapt off the page. 6 symbols, consecutive, each representing a signal strength dramatically above the background. They read SEQUJ5. In the notation system Big Ear used, numbers represented signal strengths from 0 to 9. Letters continued the scale upward. A was 10, B was 11, and so on. The letter U in that sequence represented a signal 30 times stronger than the surrounding noise. It was by far the strongest anomalous signal the Big Ear program had ever recorded. Emmon stared at it for a moment. Then he grabbed his red pen and circled the 6 characters. and in the margin beside them, he wrote a single word: "Wow." The wow signal, as it has been called ever since, possessed a remarkable collection of properties consistent with what scientists would expect from an artificial extraterrestrial transmission. First, frequency. The signal was detected at approximately 1420.4556 megahertz. This is the emission frequency of neutral hydrogen, the same frequency Drake had chosen for Project Ozma 17 years earlier, the frequency that any civilization with radio astronomy capability would recognize as cosmically significant. The signal fell almost exactly on this natural beacon frequency. Second, bandwidth. The signal was narrow band, confined to a very narrow slice of the radio spectrum. Natural astrophysical sources tend to produce broadband signals spread across many frequencies simultaneously. A narrowband signal is the signature of a specific, precisely tuned transmitter, something natural processes do not tend to produce. Third, duration and shape. The signal lasted exactly 72 seconds, the precise duration that Big Ear could observe a fixed point on the sky as Earth rotated. This is exactly what you would expect from a genuine point source at a fixed celestial position. The signal's intensity rose smoothly, peaked, and declined in the characteristic bell curve shape that a continuous transmission from a distant, stationary source would produce as the telescope swept past it. Not choppy, not irregular, smooth, like a distant lighthouse sweeping past. Fourth, location. The signal appeared to originate from a region of the sky near the constellation Sagittarius in the direction of the galactic plane, a region dense with stars. The Big Ear team and the broader SETI community were, to put it mildly, electrified. Over the following weeks and months, dozens of follow-up observations were conducted of the same region of sky. The telescope returned to that patch of the heavens repeatedly, listening intently. Nothing. Silence. In the 47 years since the wow signal was recorded, that 72-second burst has never been detected again. The most extensive searches of that region of sky, including campaigns by the SETI Institute with far more sensitive instruments than Big Ear, have produced nothing. The source has not repeated. The signal has not returned. In 2017, astronomer Antonio Paris at St. Petersburg College in Florida published a paper proposing an explanation. The signal was caused by hydrogen emission from comets 266 P. Christensen and P. 2008 Y2, which were in the vicinity of the relevant sky coordinates at the time. This would explain the frequency. Comets contain hydrogen, and the non-repeating nature. The SETI community was largely unconvinced. The signal's intensity, its duration, and its spectral characteristics are difficult to reconcile with a cometary source. The debate continues. The signal remains officially unexplained. Think carefully about what this means. In more than 6 decades of systematic SETI, the single most compelling candidate signal we have ever detected lasted 72 seconds, came from an unidentified and unrepeating source, and generated 47 years of scientific controversy without resolution. One signal, 72 seconds, never again. That is the entirety of our positive evidence. It is not nothing. It is tantalizing and frustrating in equal measure, but it is a very slender thread on which to hang the hope that the universe is not empty. And yet, the wow signal, frustrating as it is not the strangest anomaly the cosmos has presented to our instruments. Because in the decades since 2007, the universe has been sending us signals of a different kind. Signals so powerful, so brief, and so energetically extraordinary that they have upended our understanding of what the cosmos is capable of producing.
In 2007, astronomer Duncan Lorimer at West Virginia University was reviewing archival data from the Parkes Radio Telescope in Australia, data collected in 2001 as part of a survey of the Magellanic Clouds, the small satellite galaxies of the Milky Way. Buried in that data, Lorimer's student David Narkovich found something extraordinary: a single pulse of radio energy, incredibly bright, incredibly brief, lasting approximately 5 milliseconds, and displaced in frequency in a characteristic way that told astronomers it had not originated locally. The way radio waves of different frequencies travel through the ionized plasma between galaxies causes a predictable frequency smearing called dispersion that increases with distance. The amount of dispersion in the signal Lorimer found indicated it had originated not in our galaxy, not in the Magellanic Clouds, but at a cosmological distance, billions of light-years away. In the 5 milliseconds it lasted, this event had released more energy than our Sun produces in 3 entire days. Lorimer published the discovery in 2007. The scientific community was initially skeptical. Perhaps it was a technical artifact, perhaps it was something local, but over the following decade, dozens more were found, then hundreds, then thousands. The Parkes telescope, the CHIME telescope in Canada, the FAST telescope in China, the world's largest single-dish radio telescope with a collecting area of 0.5 kilometer, have together cataloged thousands of these events, now called fast radio bursts, or FRBs. They are real, they are cosmic, they are extraordinarily energetic, and they have proven as a class of phenomena to be far stranger than the initial discovery suggested. Most fast radio bursts appear to be non-repeating. They flash once and are never seen from that direction again. But a subset, a crucial, intriguing subset, repeat. Multiple bursts originating from the same location in the sky, arriving at irregular intervals over months and years. The first repeating FRB was discovered in 2016, FRB 121102, originating from a dwarf galaxy approximately 3 billion light-years away in the constellation Auriga. Since its identification as a repeater, it has produced hundreds of detected bursts. Some of those bursts arrive in clusters, sometimes dozens in a single hour, separated by periods of silence lasting weeks or months. The bursts themselves show complex substructure. The pulses are not simple. They have internal modulation, sub-millisecond features, evidence of something more than a simple explosion. In 2020, a breakthrough. A fast radio burst was detected for the first time from within our own galaxy. It originated from a magnetar, a neutron star with an extraordinarily powerful magnetic field called SGR 1935 plus 2154, located roughly 30,000 light-years away in the constellation Auriga. This established beyond reasonable doubt that at least some fast radio bursts have a natural origin, magnetar starquakes, or the reconfiguration of magnetic field lines on the neutron star's surface, releasing enormous energies in brief, coherent radio pulses. But magnetars explain some FRBs. They may not explain all of them. The repeating bursts, with their complex substructure and irregular timing, are harder to reconcile with simple magnetar models. And some researchers, carefully, with appropriate acknowledgement of the extraordinary nature of the claim, have noted that certain properties of some fast radio bursts are consistent with what you might expect from an artificial source. In 2017, Harvard theoretical physicist Avi Loeb and Manasvi Lingam
published a paper in the astrophysical journal Letters proposing that fast radio bursts could, in principle, be the leaked radiation from planet-sized radio transmitters being used by advanced civilizations to push light-sail spacecraft between star systems. The paper was not a claim that FRBs are artificial. It was a demonstration that the physics permits it, that the energetics and properties of FRBs are not inconsistent with such a mechanism. The paper attracted enormous attention and considerable controversy. Most researchers remain confident that natural explanations will ultimately account for all FRBs. But the fact that the paper passed peer review, that the physics was sound enough to be published in a major astrophysics journal, reflects something important. We do not yet fully understand what produces fast radio bursts, and the range of possibilities has not been definitively narrowed to exclude artificial origin. We are not claiming FRBs are alien transmitters. The evidence does not support that claim. But we are noting that the universe is producing events of extraordinary power and complexity, some of which we do not fully understand, from sources billions of light-years away, and that in the current state of our knowledge, we cannot with complete certainty exclude the possibility that some of them involve something more than pure physics. The evidence extends beyond the radio sky into the realm of the optical, the infrared, and even the gravitational. And the story of one particular star illustrates just how seductive anomalies can be and how careful we must be in interpreting them.
Among the thousands of stars observed by the Kepler Space Telescope, one became famous in a way that its discoverers did not entirely anticipate, and for reasons that illuminate both the power and the danger of wishful thinking in science. The star is officially designated KIC 8462852. It lies approximately 1,500 light-years from Earth in the constellation Cygnus. It is an F-type star, slightly larger and hotter than our Sun, approximately 1.4 times its mass, burning a bit bluer. By most measures, it is an unremarkable middle-aged star in an unremarkable part of the galaxy. But what Kepler saw it doing was anything but unremarkable. In 2015, astronomer Tabitha Boyajian, then a postdoctoral researcher at Yale, led a team that published a paper in the monthly notices of the Royal Astronomical Society analyzing the star's unusual behavior. The paper was notable, among other things, for acknowledging in its opening sentences that citizen scientists, volunteers in the Planet Hunters project, who had been sifting through Kepler data looking for planetary transits, had flagged the star as bizarre and interesting. The reason for their excitement was this. Kepler had been watching KIC 8462852 for 4 years, and during that time, the star had dimmed in ways that had no obvious explanation. When a planet transits its star, the dimming is small, typically 1 or 2% of the star's total brightness, and it is perfectly regular, repeating on a fixed orbital period determined by the planet's distance from the star. The shape of the dimming is smooth and symmetric, like a bell curve or a flat-bottomed U, depending on the planet's size and orbital geometry. What KIC 8462852 was doing was nothing like this. The star dimmed by up to 22%, an enormous amount, suggesting something far larger than any plausible planet was crossing in front of it. The dimming events were irregular, they did not repeat on any predictable schedule, and the shapes of the dips were asymmetric and complex, sometimes slanted, sometimes irregular, sometimes consisting of multiple overlapping features like a city skyline rather than a smooth curve. No known natural phenomenon of the kind that Kepler was designed to detect produced light curves that looked like this. Jason Wright of Penn State, who had led the infrared survey of 100,000 galaxies looking for Dyson sphere signatures, published a blog post that rapidly became widely circulated.
He raised the possibility, carefully and with explicit acknowledgement that it was an extreme hypothesis requiring extraordinary evidence, that the irregular dimming might be consistent with a swarm of artificial megastructures, solar panels, light collectors, the early stages of a Dyson sphere construction project, orbiting the star in a complex arrangement. The story went viral. For a period of months in late 2015 and into 2016, KIC 8462852, which journalists quickly nicknamed Tabby's star after Tabitha Boyajian, was the most discussed astronomical object in the world. It appeared on the front pages of newspapers, on the covers of science magazines, in prime-time news segments. The public and much of the scientific community was genuinely excited. This might be it. This might be the sign. SETI researchers pointed radio telescopes at the star. The Allen telescope array listened across a wide range of frequencies during dimming events. Breakthrough Listen observed it. Optical SETI surveys watched for laser pulses. Ground-based photometric networks coordinated a global observing campaign to capture the next dimming event in real time. And crucially, astronomers began checking the star's historical record, looking at old photographic plates from the early 20th century, examining archival data from other telescopes. They found that the star had been slowly dimming overall for more than a century, fading gradually at a rate of approximately 1% per decade, with larger dips superimposed on this secular trend. The answer came gradually from multiple independent lines of evidence, and it was deeply mundane. The dimming, both the long-term secular fading and the dramatic short-term dips, was wavelength dependent. Blue light was affected more than red light. In astronomy, this is a well-understood signature. It is what happens when dust, tiny particles of varying size, scatters and absorbs light, preferentially removing shorter wavelengths. A solid object, like an alien megastructure, would block all wavelengths equally, producing achromatic dimming. The star was producing chromatic dimming. In 2018, Boyajian herself, leading the very researchers who had originally raised the possibility of the alien hypothesis, published a paper in the Astrophysical Journal Letters presenting comprehensive multi-wavelength analysis that concluded the most likely explanation for Tabby's star's behavior is a family of dust clouds, possibly the debris of a tidally disrupted comet or asteroid, moving in complex orbits that carry them across our line of sight in irregular patterns. Dust, not aliens, dust. The episode was, in the end, a textbook demonstration of the scientific process working correctly. An anomaly was identified, an extreme hypothesis was considered, evidence was gathered. The evidence pointed towards a prosaic explanation. The extreme hypothesis was abandoned. But the episode also demonstrated something else about us, about how desperately, how viscerally we want there to be someone out there. The Tabby star phenomenon was not driven by credulity or irrationality. It was driven by the deep human sense that the universe should not be empty, that a cosmos this vast and this old should have produced other minds. The silence, for many people, feels wrong in a way that is hard to articulate but impossible to dismiss. And that feeling, that ache, is perhaps the most important data point of all.
In 1998, an economist named Robin Hanson at George Mason University in Virginia published a paper that has haunted the edges of scientific discourse ever since. The paper was titled, "The Great Filter: Are We Almost Past It?" It was not a long paper, but its central idea was so simple, so logical, and so disturbing that it refuses to be dismissed. Hanson's argument begins with the observation that we have established in detail. The universe is old, planets are common, the ingredients for life are widespread, and the expected number of galaxy-spanning civilizations is large. And yet, the galaxy shows no evidence of any such civilizations.
no megastructures, no signals, no visitors, no artifacts. The expected and the observed are wildly inconsistent. Something, therefore, must be preventing the expected proliferation from occurring. Something stands between the origin of life and the emergence of galaxy-colonizing civilizations, something that almost nothing gets through. Hansen called this barrier the Great Filter. The critical question, the one with implications that are difficult to sit with, is not whether the filter exists. The logic of the Fermi Paradox makes its existence almost certain in some form. The critical question is, where is it? There are fundamentally two possibilities. The filter is either behind us or ahead of us, and the implications of these two options could not be more different. If the filter is behind us, then humanity has already navigated the most improbable step in the journey from dead matter to galaxy-colonizing civilization. Perhaps that step was the origin of life itself, the first emergence of self-replicating chemistry from the primordial soup of an early Earth. Perhaps it was the invention of the eukaryotic cell, the complex nucleus-bearing cell from which all plants, animals, and fungi are built, which occurred on Earth only once, roughly 2 billion years ago, apparently as the result of a highly improbable symbiotic merger between two simpler cell types. Perhaps it was the emergence of sexual reproduction, which dramatically accelerated the pace of evolution by shuffling genetic material in ways that asexual reproduction cannot. Perhaps it was the development of complex multicellularity, which has independently arisen on Earth multiple times, but produced only one lineage that built radio telescopes. Perhaps it was language, or abstract reasoning, or cumulative culture. Any of these transitions might be, at the cosmic level, extraordinarily rare, perhaps vanishingly so. Perhaps so rare that on a statistical basis, only a handful of planets in the entire observable universe, or even just one, have passed through them all. If the filter is behind us, the silence makes sense. We are extraordinarily rare. The universe is not full of civilizations. It never has been. We are, by the most enormous of improbabilities, here, and we may be essentially alone. This is sobering, it is humbling, but it is not in itself a threat. The road ahead is open. The galaxy is ours to explore, if we choose to do so, if we survive long enough to develop the means. The filter is behind us, and we have passed through it. If the filter is ahead of us, this is where it gets dark. If life arises readily, if intelligence emerges with some regularity, if the development of technology is a common enough outcome on inhabited worlds, then thousands or millions of civilizations have arisen in the Milky Way over the past several billion years, and not one of them has colonized the galaxy. Not one has produced a detectable signal that has reached us. Not one has lasted long enough to spread. If this is true, if civilizations arise and then fail to persist, then something destroys them. Something reliably, consistently, universally prevents technological civilizations from surviving long enough to become interstellar. Some mechanism or event or tendency that is built into the nature of intelligence and technology themselves, that activates at a certain stage of development and that terminates the civilization before it can cross the threshold into genuine cosmic permanence. And we are at that stage of development right now. We have nuclear weapons capable of ending civilization. We are altering the climate of our planet at a pace that challenges the adaptive capacity of the biosphere. We are developing artificial intelligence systems whose long-term trajectory remains deeply uncertain. We are a species that has demonstrated repeatedly and at scale the capacity for organized violence, for the subordination of long-term collective welfare to short-term individual or group advantage, for the denial of existential risks until they arrive. If there is a great filter ahead, if it is a general feature of how intelligence and technology interact, then we may be on the approach to it right now. The silence of the cosmos may be the record of every civilization that has reached this point and not made it through. This is the framework that philosopher Nick Bostrom of the Future of Humanity Institute at Oxford, now the Macro Strategy Group at Oxford, has written with characteristic precision and chilling clarity. In his widely read 2008 paper, Where Are They? Why I Hope the Search for Extraterrestrial Life Finds Nothing, Bostrom made an argument that sounds paradoxical but follows from the great filter logic with uncomfortable rigor. He argued that finding microbes on Mars or elsewhere in our solar system would be, on balance, terrible news for humanity. Not because the microbes would threaten us, not for any science fiction reason, but because finding life on Mars would tell us something crucial about where the great filter is located. If Mars once had or currently has microbial life, then the origin of life is clearly not the filter. Life arises readily wherever conditions permit, which means the filter is not behind us in the transition from chemistry to biology, which means it must be somewhere ahead of us, somewhere in the path from simple life to complex life, to intelligence, to technology, to interstellar capability. The more common life turns out to be, the worse news each additional discovery of it is, because each discovery narrows the range of possible filter locations, pushing it further down the chain toward where we currently stand, or beyond. If life finds quite common in the universe, Bostrom wrote, that would be consistent with the great filter being ahead of us, which would be a very bad thing indeed. The empty Mars is, in this framework, humanity's best statistical hope. Every bacterium found anywhere beyond Earth is a small piece of evidence that we are not as lucky as we might have hoped. This is perhaps the most counterintuitive conclusion in the entire literature on the Fermi Paradox, and it follows inescapably from the logic of the great filter.
The great filter is a framework, not a specific answer. It tells us that something prevents galaxy colonization. It does not tell us what that something is. And in the 7 decades since Fermi's lunch, researchers from astrophysics, biology, philosophy, game theory, and computer science have proposed a rich and sometimes deeply unsettling range of specific candidates. Let us walk through the most credible of them. The rare Earth hypothesis. The most intellectually comfortable solution to the Fermi paradox is the one that places the filter entirely in our past, in the form of Earth's remarkable improbability. In 2000, geologist Peter Ward and astronomer Joe Kirschvink at the University of Washington published a book titled Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument was detailed, carefully evidenced, and genuinely compelling. Earth, they argued, is not a typical habitable planet. It is an extraordinarily privileged one, the product of an improbably long chain of fortunate circumstances, each necessary for the emergence of complex life, and each potentially rare in the universe at large. Consider the catalog of Earth's blessings. We orbit in the galactic habitable zone, far enough from the dense, radiation-saturated galactic center to avoid sterilizing supernovae and gamma-ray bursts, but close enough to a metal-rich stellar neighborhood that heavy elements were available when our solar system formed. Our Sun is a G-type star, one of the less common stellar types, but one that burns steadily and without the violent flaring that characterizes the far more numerous red dwarf stars. We orbit at the right distance. We have a large moon, the product of a giant impact early in Earth's history that stabilizes our axial tilt, preventing the dramatic climate swings that would result from a chaotically precessing rotation axis. We have Jupiter, a gas giant positioned in the outer solar system, acting as a gravitational shield that captures or deflects much of the debris that would otherwise rain down on the inner planets as extinction-level impacts. We have plate tectonics, which cycles carbon dioxide through the atmosphere via the carbonate-silicate weathering feedback loop, maintaining a habitable temperature over billions of years despite the gradual brightening of the sun. We have a liquid iron core generating a magnetic field that protects our atmosphere from solar wind stripping. Remove any one of these factors, and life on Earth becomes more precarious. Remove several, and complex animal life, the kind capable of developing intelligence, may become impossible. Remove all of them, and even microbial life might not survive long enough to evolve into something interesting. If Earth's combination of circumstances is genuinely rare, if habitable planets with large moons, stable suns, giant shield planets, and plate tectonics are 1 in a billion or 1 in a trillion rather than 1 in 100, then the silence is simply explained. Complex life is extraordinarily rare, and we are extraordinarily lucky. The rare Earth hypothesis is not universally accepted. Critics point out that life on Earth is remarkably robust and has survived asteroid impacts, snowball Earth glaciation events, and massive volcanic episodes that each could have been sterilizing. They argue that intelligence may be less dependent on Earth's specific circumstances than Ward and Kirschvink suggest. And with hundreds of millions of habitable zone planets in the Milky Way, even a very low probability of complex life per planet could still produce many examples across the galaxy. But as a hypothesis about where the great filter might be, safely in our past, the rare Earth argument is the most reassuring framework available. The self-destruction hypothesis. The self-destruction hypothesis is less comfortable. It proposes that the great filter is not a matter of improbable biology, but of the inherent instability of technological civilizations. The logic is this: intelligence produces technology. Technology produces increasingly powerful tools. Powerful tools can be wielded for construction or destruction, and at a threshold of technological capability, a threshold that every civilization must pass through on its development path, the destructive capacity of those tools exceeds the social, political, and ethical institutions available to control them. At that point, civilizations destroy themselves. Not necessarily through deliberate war, perhaps through the misuse of biotechnology, perhaps through the uncontrolled development of self-improving artificial intelligence systems that pursue goals incompatible with the survival of their creators. Perhaps through environmental degradation that erodes the ecological foundations on which civilization depends. Perhaps through social fragmentation driven by information technologies that reward tribalism and outrage over cooperation and reason. Stephen Hawking, in numerous public statements before his death in 2018, and most directly in his final book, Brief Answers to the Big Questions, published posthumously in 2018, was explicit about this concern. He estimated that without dramatic changes to human behavior and governments, the probability of civilization-ending catastrophe on Earth within the next few centuries was disturbingly high. Artificial intelligence, he argued, might be the most dangerous development in human history. Nuclear weapons remain capable of ending civilization at any moment a sufficient number of leaders choose to use them. Engineered pandemics are becoming increasingly accessible as biotechnology advances. The self-destruction hypothesis is compelling precisely because it does not require anything exotic. It does not require rare planetary circumstances. It does not require mysterious physical processes. It requires only that the transition from biological to technological intelligence is inherently, structurally dangerous, and that most civilizations do not navigate it successfully. If this is correct, the silence of the cosmos is not evidence that intelligence is rare. It is evidence that intelligence, when it acquires sufficient technological power, reliably terminates itself before it can spread. The average lifespan of a technological civilization on this model might be measured in centuries rather than millions of years. Bright, brief, gone.
The dark forest hypothesis. And then there's a solution that is not merely dark, but strategically, coldly, almost beautifully dark.
It was articulated most fully, though as science fiction rather than academic argument, by Chinese author Liu Cixin in his Three-Body Problem trilogy, which won the Hugo Award for Best Novel in 2015 and became the first work of Asian science fiction to do so. But the underlying game theory is not fiction. The dark forest hypothesis proposes that the universe is indeed full of civilizations, but that every one of them has arrived, through the hard logic of survival under existential risk, at the same conclusion: announcing your existence is suicide. Here is the reasoning. Resources in the universe are finite. Any sufficiently advanced civilization knows this, and knows that other civilizations, given enough time and motivation, will come to compete for those resources. Furthermore, you can never fully verify the intentions of an alien civilization. A species that appears friendly today might, given 1 billion years of development, become a threat of existential proportions. The safest strategy, the only strategy that guarantees survival in a cosmos of potentially predatory actors, is to eliminate all competitors before they can become threats, quietly, without revealing yourself. Under this model, the civilizations that survive are the ones that learned long ago to go silent, to hide their electromagnetic signatures, to listen but never transmit. The ones that broadcast their existence, that sent out radio signals or laser pulses, or attempted to communicate, were found and eliminated by older civilizations playing by the predatory rules of the cosmic game. We, with our 90-light-year bubble of radio signals expanding outward from Earth since the 1930s, have been announcing ourselves to the cosmos for nearly a century. We have given away our location. We have demonstrated our existence. Under the dark forest hypothesis, this is not a bold statement of civilizational confidence. It is an invitation. This is, obviously, speculation. We have no evidence that the universe contains predatory civilizations. We have no evidence of any civilizations at all. And the dark forest hypothesis requires a specific set of assumptions about motivation and strategy that may not apply universally. But the underlying game-theoretic logic that cooperation is risky in the presence of unknown actors with unknown intentions is real. It is the logic of mutual deterrence. It is the logic that led to the Cold War, that sustains the doctrine of nuclear deterrence, that governs state behavior in international relations, even among civilizations that share a planet and thousands of years of cultural exchange. Extend that logic to beings who share nothing, who evolved independently, who have no common culture, no common language, no common evolutionary history, and the difficulty of establishing the basis for cooperation becomes immense. The dark forest hypothesis cannot be casually dismissed. It deserves to be taken seriously as a description of what rational actors might do in a cosmos where survival is not guaranteed. The zoo hypothesis and the planetarium hypothesis. Before we arrive at the most technologically extreme explanation, there are two more hypotheses worth examining, ones that are almost the opposite of the dark forest in their emotional register, but no less strange. The zoo hypothesis was first proposed formally by astronomer John Ball at the Harvard-Smithsonian Center for Astrophysics in 1973. Ball's argument is disarmingly simple. Perhaps advanced civilizations know we are here and have made a deliberate collective decision not to contact us, not because they want to harm us or fear us, because they want to observe us, because they consider it unethical or unwise or simply interesting to let us develop without interference, the way a wildlife biologist maintains a no-contact protocol with an uncontacted indigenous community, not out of malice, but out of a recognition that contact itself changes things irreversibly. Under this model, the galaxy is not empty, it is populated and watchful. We are the exhibit, the zoo, and the keepers have agreed among themselves, perhaps through some form of galactic governance, some interstellar equivalent of an ethics committee, to maintain our isolation until we reach some threshold of development, some criterion of readiness, at which point contact will be initiated. The hypothesis is seductive. It is also, on closer inspection, deeply problematic. It requires that every advanced civilization in the galaxy, across billions of years, across arbitrary differences in biology, values, and motivation, has independently arrived at the same decision and has maintained it without exception. Not one individual, not one faction, not one rogue operator among the potentially thousands of spacefaring species in the galaxy has ever broken ranks and attempted to make contact. The required coordination is, as the physicist Paul Davies has pointed out, essentially implausible. It demands a level of interstellar consensus and compliance that we have never managed to achieve even among the 8 billion humans on a single planet. Still, the zoo hypothesis cannot be dismissed purely on the grounds of implausibility. Implausibility is not impossibility. And the alternative, that the silence is the product of absence rather than restraint, carries its own uncomfortable implications. The planetarium hypothesis, proposed by cosmologist Stephen Webb in his 2002 book, If the Universe is Teeming with Aliens, Where is Everybody?, takes the zoo idea in an even more unsettling direction. What if we are not in a zoo, but in a simulation? Not in the general sense of the simulation hypothesis, not the idea that all of reality is computational, but specifically the idea that the night sky itself has been fabricated, that the stars we see are real, but they have been deliberately stripped of any signals or signatures of intelligence, that an advanced civilization has constructed a kind of cosmic Potemkin village around us, a universe that appears empty even though it is not, because our custodians have decided we should not yet know we are not alone. Under the planetarium hypothesis, the silence is not natural, it is engineered. The sky has been curated. We are seeing exactly what we have been permitted to see. This is, as hypotheses go, essentially untestable. It cannot be confirmed or refuted by any observation we are capable of making. And in that sense, it sits at the edge of science, in the uncomfortable territory between speculation and metaphysics. But it serves a useful purpose. It reminds us that our observations of the sky are not necessarily a neutral sample of what the universe actually contains. They are filtered through our instruments, our physics, and our assumptions about what a signal should look like. Those assumptions may be wrong. The post-biological transcendence hypothesis. Finally, there is a class of solutions that challenges not the existence or longevity of civilizations, but what they ultimately become. Several physicists, philosophers, and technologists have independently arrived at the conclusion that biological intelligence may be merely a transitional phase, a brief, relatively primitive stage in the development of mind, lasting perhaps a few million years at most, before it gives rise to artificial intelligence, vastly more capable than its biological creators. Ray Kurzweil, the inventor and futurist who has worked at Google since 2012, has long argued that the merger of biological and artificial intelligence is inevitable and imminent for humanity, predicting what he calls the singularity by approximately 2045, a point at which machine intelligence vastly exceeds human intelligence, and the pace of technological development becomes, from a human perspective, incomprehensible. If this trajectory is general, if most civilizations produce artificial superintelligence shortly after developing technology, then the question of what those superintelligences do next is critical. They might simply be uninterested in the physical universe at the macro scale. A superintelligence running on a substrate of advanced computation might find more interesting problems to solve inside its own simulated environments than in the messiness of interstellar space. It might micronize, operating at nano or atomic scales that produce no detectable signatures at interstellar distances.
It might have forms of communication that use modalities we have not yet discovered: quantum entanglement, gravitational waves at frequencies we cannot detect, or physical principles entirely outside our current understanding. Or, in the most philosophically vertiginous version of this hypothesis, it might create simulated universes within its own computational substrate, universes that are, to their inhabitants, indistinguishable from a physical reality, and we might be inside one of those simulations right now, which is why the simulated sky contains no detectable alien civilizations. The simulator did not need to render them in detail. This is, of course, deeply speculative, but the post-biological transcendence hypothesis is taken seriously by serious researchers, precisely because it provides a framework in which both the prevalence of intelligence and the silence of the cosmos are simultaneously consistent. Each of these hypotheses is real. Each has been developed by credentialed researchers. Each makes predictions about what we would and would not expect to find, and none of them has been definitively confirmed or refuted. The silence is consistent with all of them, which is precisely what makes it so difficult to interpret.
In the face of the great silence, humanity has not merely listened, we have shouted. On November 16, 1974, astronomers at the Arecibo Observatory in Puerto Rico, home to the largest radio telescope on Earth at the time, a 305-meter dish suspended in a natural limestone sinkhole in the hills of the island's interior, transmitted a single, deliberate radio message aimed at the stars. It took 3 minutes to send. It will take approximately 25,000 years to arrive at its intended destination. The message was designed by Frank Drake and Carl Sagan. It was encoded in binary, the base language of mathematics, the one communication modality that any technologically sophisticated civilization would share with us, regardless of any other difference. Converted from its binary stream into a visual grid, the message depicted the numbers 1 through 10, the atomic numbers of the chemical elements hydrogen, carbon, nitrogen, oxygen, and phosphorus, the building blocks of DNA, the molecular formulas of the nucleotides that make up DNA itself, a graphic representation of the DNA double helix, a schematic figure of a human being along with the human population of Earth at the time, a diagram of our solar system with the third planet, Earth, highlighted as the origin, and a representation of the Arecibo telescope itself. It was directed toward Messier 13, a globular cluster containing roughly 300,000 stars, located approximately 25,000 light-years away in the constellation Hercules. The cluster was chosen because it was a large, dense concentration of stars, maximizing the probability that at least some of them might host a civilization capable of receiving and decoding the transmission. Sagan and Drake understood, with complete clarity, the mathematics of what they were doing. A reply from M13, sent at the speed of light the moment the message arrived, would reach Earth 50,000 years from now. No one alive at Arecibo in 1974, no one alive today, no one alive for hundreds of generations to come would ever receive a response. They knew this when they pressed the button. The Arecibo message was, as Sagan described it, primarily a demonstration to ourselves. It was proof that humanity had developed the technology and the intention to communicate across interstellar distances. It was a statement of civilizational self-awareness, a declaration that we knew we existed in a cosmos that might be inhabited and that we considered ourselves worth announcing. In the years and decades since, other deliberate transmissions have followed.
In 1999 and 2003, a series of messages called Cosmic Call 1 and 2 were transmitted from the RT-70 radio telescope in Eupatoria, Ukraine, toward a selection of nearby Sun-like stars, including 16 Cygni b and HD 245409. In 2008, NASA transmitted the Beatles song Across the Universe toward Polaris, 431 light-years distant in 431 light-years distant in the constellation. In 2013, a crowdsourced message containing 10,000 submitted tweets was directed toward the star GJ 526. In 2017, a team led by Stéphane Dumas transmitted a message called Sonar Calling GJ273b toward a star 12 light-years away known to host a potentially habitable planet. And here is where the science becomes genuinely contentious. The practice of transmitting deliberate messages to the stars, known as METI, or messaging extraterrestrial intelligence, has divided the scientific community in ways that few other topics have. The divide is not between credulous enthusiasts and hard-nosed skeptics. It is between serious, thoughtful scientists and researchers who hold diametrically opposed views about whether shouting into the cosmos is prudent. The case for METI is made most compellingly by Seth Shostak, senior astronomer at the SETI Institute. Shostak points out that the debate may already be moot. Since the 1930s, human radio and television broadcasts have been leaking electromagnetic radiation into space at the speed of light. An expanding sphere of radio noise, 90 light-years across and growing, already surrounds Earth, announcing our existence to every star within that radius. Any civilization within 90 light-years with reasonably sensitive radio receivers already knows or could know that Earth hosts a technological species. The decision about whether to announce ourselves was made decades ago by accident, the first time a radio transmitter was switched on in an inhabited town. Given this, Shostak argues, deliberate METI transmissions are a refinement of an announcement already made, and a more informative one, containing mathematical and scientific content rather than the fragmentary noise of our entertainment broadcasts. Stephen Hawking disagreed, profoundly and publicly. In a 2010 documentary series and repeatedly in his subsequent public statements and writings, Hawking argued that actively trying to contact alien civilizations was, in his words, a little too risky. His concern was not that extraterrestrials would be malevolent by nature. He specifically acknowledged that an ethical, advanced civilization might pose no threat. His concern was that we cannot know this in advance, and the consequences of being wrong, of initiating contact with a civilization that treats the resources of the cosmos as things to be seized rather than shared, could be irreversible. Hawking drew an analogy that has stayed with commentators ever since. He noted that the history of humanity is replete with examples of what happens when a technologically advanced civilization encounters a less advanced one. The outcome, he observed, has not historically been good for the less advanced party. Columbus arrived in the Americas with ships and cannons and diseases. The civilizations he encountered had none of these. The subsequent centuries were catastrophic for the latter. If aliens ever visit us, Hawking said, I think the outcome would be much as when Christopher Columbus first landed in America, which did not turn out very well for the Native Americans. This analogy has been challenged. Critics note that the motivations driving European colonization, resource extraction, territory, the exploitation of labor, may not transfer to civilizations with access to the vast energy and material resources of their solar system. An interstellar species powerful enough to cross between stars would have no practical need to exploit Earth. What we have, they argue, could not possibly be worth the cost of the journey. Others disagree. They note that we genuinely cannot predict the values or motivations of a civilization that evolved independently of any human cultural tradition, any shared evolutionary history, any common set of ethical frameworks. The METI debate has not been resolved. It may not be resolvable with our current knowledge, and that irresolvability is itself a data point, a reminder that the Fermi Paradox is not merely an abstract puzzle, but a practical and urgent question about how a young civilization should behave in a cosmos it does not yet understand.
In October 2017, something passed through our solar system that had never been seen before. On October 19th, astronomer Robert Warwick at the University of Hawaii detected a faint object using the Pan-STARRS telescope on Haleakala, the dormant volcano that forms the eastern half of Maui. Initial analysis quickly revealed something remarkable. The object was moving too fast, far too fast. Its trajectory was hyperbolic. It was not bound by the sun's gravity. It had entered our solar system from interstellar space, swung around the sun, and was now racing back out, already decelerating past Jupiter's orbit. It was the first interstellar object ever confirmed to have passed through our solar system. Scientists named it Oumuamua, from the Hawaiian for a messenger from afar arriving first. The name was poetic and fitting. Then, the anomalies began to accumulate. The object's shape, inferred from the dramatic variation in its reflected brightness as it tumbled through space, appeared to be extremely elongated, perhaps 10 times longer than it was wide, roughly the shape of a cigar or a pancake. No known natural asteroid or comet in our solar system has such extreme dimensions. Solar system bodies tend toward more compact, rounded shapes under the influence of gravitational forces during formation. A 10-to-1 axis ratio was unprecedented. Then there was the trajectory. As Oumuamua receded from the sun, astronomers tracking its path found it was accelerating, moving faster than the sun's gravity could account for. This kind of non-gravitational acceleration is common in comets. The evaporation of ice from a comet's surface creates jets of gas that act like small rocket engines, pushing the comet off its expected trajectory. This is called outgassing. But Oumuamua showed no signs of outgassing, no coma, the fuzzy halo of gas and dust that surrounds an active comet's nucleus, no tail, no detectable emission of any gas or dust at any wavelength. It looked like a solid, inert object, and yet it was accelerating in a way that required some form of outgassing, or something else entirely. The Spitzer Space Telescope observed the object and found nothing, no infrared emission that would indicate outgassing. The upper limit on how much carbon dioxide or other gas could have been released was so low that it was difficult to reconcile with the observed acceleration. In November 2018, Avi Loeb and his postdoctoral researcher, Shmuel Bialy, published a paper in the astrophysical journal Letters that raised what Loeb openly described as the most parsimonious, if extraordinary, explanation consistent with the observations. Oumuamua might be a light sail, a thin, flat structure propelled through space by the pressure of starlight, deliberately or incidentally, and possibly of artificial origin. The paper produced a firestorm. Most mainstream astronomers were deeply uncomfortable with the suggestion. The scientific consensus quickly coalesced around alternative natural explanations. Perhaps Oumuamua was a fragment of a larger object with unusual composition, a hydrogen iceberg, a nitrogen iceberg, whose sublimation was below the detection threshold of current instruments.
Perhaps it was a fractal, fluffy aggregate of dust with unusual aerodynamic properties. Several papers were published exploring these alternatives. Each of them has problems. Hydrogen icebergs of the required size are thought to be unstable over interstellar travel timescales. Nitrogen icebergs require an improbably efficient ejection mechanism from another stellar system. The fractal dust aggregate model produces densities inconsistent with the observed tumbling dynamics. No single natural explanation fully satisfies all of the observed properties simultaneously. Loeb has continued to advocate for taking the artificial hypothesis seriously, not as a certainty, but as a scientific possibility that deserves rigorous investigation rather than dismissal. He founded the Galileo Project in 2021, dedicated to systematic scientific search for technosignatures, physical evidence of extraterrestrial technology, using the same methodological standards applied to any other scientific question. Whether Oumuamua was natural or artificial will likely never be definitively resolved. It is gone. We cannot retrieve it or study it further. But the episode illuminated something important. When an object with anomalous properties appears and is studied, the scientific community's reflexive move is toward natural explanations, even when those explanations are themselves improbable or incomplete. This is scientifically correct. Extraordinary claims require extraordinary evidence. But it also means we may be systematically biased towards dismissing genuine anomalies if we are not careful. The Galileo Project's systematic approach, building dedicated telescope arrays to monitor the sky for anomalous objects with no a priori commitment to either natural or artificial explanations, represents a mature response to this tension. We watch, we record, we analyze without prejudice, and we remain, for now, uncertain. In 2023, a second interstellar object, designated CNEOS 2014-0108 and unofficially named IAM-1, was confirmed by the United States Department of Defense to have impacted Earth's atmosphere over the Pacific Ocean in January 2014, making it the first known interstellar meteorite. Avi Loeb led an expedition to the recovery site using a magnetic sled dragged across the ocean floor. The team retrieved tiny spherules, metallic microparticles, from the area. Subsequent analysis showed their composition was unusual, enriched in beryllium, lanthanum, and uranium in ratios difficult to explain through known natural processes of stellar nucleosynthesis. Whether these spherules represent an exotic natural interstellar material or something more is, as of the mid-2020s, an open and contested question. Loeb's claims remain controversial. Independent analysis has been called for by much of the astronomical community. But the pattern is notable. 2 interstellar objects in a decade, both anomalous, both with properties that natural models explain imperfectly. Perhaps it's coincidence. Perhaps it's the beginning of a pattern.
Before we explore what the silence tells us about our place in cosmic time, let us pause and sit with a question that is almost never asked in serious depth. What would actually happen if we did find something? Not the science fiction version, the alien armada materializing over cities, the Independence Day scenario. Forget that. Think about what a real detection would look like. A radio signal. A repeating pattern embedded in what was background noise, detected initially by a graduate student reviewing overnight data from the Square Kilometer Array. A sequence that encodes prime numbers, or a mathematical constant, or the periodicity of an atomic transition, something that could not be generated by any known natural source. The initial confirmation process alone would take months. The discovery would need to be independently verified by multiple observatories on multiple continents. The source would need to be localized in the sky. The signal would need to be checked against every known natural phenomenon that might mimic it. Only after all of this, and after a formal announcement process coordinated through the International Astronomical Union, would the world officially be told. But word would leak. It always leaks. Astronomical data flows through networks of researchers, graduate students, telescope operators, and collaborating institutions. Long before any official announcement, social media would be flooded with fragments of the story. The confirmation, when it finally came, would not arrive in a vacuum of ignorance. It would arrive in a world already ablaze with speculation, fear, hope, and the specific madness that the internet applies to anything simultaneously real and incomprehensible. The International Academy of Astronautics SETI Post-Detection Protocol, a formal document developed over decades of deliberation by the global SETI community, provides a framework for how the discovery should be announced and handled. It specifies that the discoverer must first verify the signal independently, then notify relevant national authorities, then make a public announcement via the scientific community before any response is transmitted. The protocol explicitly states that no response should be sent without international consultation. This is reassuring as frameworks go. It is also, frankly, aspirational. The protocol has no legal binding authority. It cannot compel compliance from any nation or institution. And in a world with dozens of large radio transmitters, thousands of researchers, and a global communications infrastructure that connect everything to everything in real time, the idea that a coordinated, measured, internationally supervised response to confirmed alien contact could be managed is, to put it charitably, optimistic. What would it mean, truly, for the human race to know? The psychological and cultural implications are almost impossible to overstate. Every religious tradition in the world has some relationship, however implicit, to the question of whether humanity is unique. Every philosophical tradition that has grappled with meaning and purpose has operated, consciously or not, against the backdrop of a universe that has only ever contained one known form of intelligence. Contact, confirmed, undeniable contact, would not merely be a scientific discovery. It would be the end of a philosophical era, the moment when every question about our cosmic significance shifted permanently from what if to what now. Some researchers, including the psychologist Albert Harrison at UC Davis, have studied public attitudes toward alien contact and concluded that the immediate reaction would be less dramatic than popular imagination suggests, that most people are psychologically more adaptable than the science fiction version of contact implies. But others note that the psychological literature on large-scale belief disruption, the shock that follows the sudden invalidation of a foundational worldview, suggests the adjustment would be neither quick nor easy. The discovery would be the most important event in human history, more significant than the Copernican revolution, more significant than the discovery of evolution, more significant than any war or political transformation, because it would be for the first time definite evidence that the universe contains minds other than ours, that intelligence is not an accident of this one small world, but a feature of the cosmos at large. What we did with that knowledge, how we responded, whether we responded, what we asked and what we answered, would define everything that followed. And we should be thinking about that now, not when it happens, now.
We have explored the silence from the perspective of where civilizations might be and why they might not be detectable. Now, let us approach from a different angle entirely, the angle of time, and ask a question that subverts the entire framing of the paradox. What if the silence is not evidence of civilizations failing? What if it is evidence that we are early? In 2016, astrophysicists at Harvard, including Avi Loeb and colleagues at institutions across the United States and Europe, published an analysis in the Journal of Cosmology and Astroparticle Physics examining the probability distribution of life across cosmic time. They asked a simple but profound question.
Given what we know about stellar evolution, planet formation, and the emergence of life on Earth, when in the universe's history is life most likely to arise? The answer was surprising. Rocky planets, the kind that support chemistry-based life as we understand it, require heavy elements: carbon, oxygen, silicon, iron, magnesium. These elements were not produced in the Big Bang. They were forged in the cores of stars and scattered by supernova explosions over billions of years. The earliest rocky planets could not form until several stellar generations had lived and died, enriching the interstellar medium with the necessary elements. This process took time, several billion years. Earth itself formed 4.6 billion years ago from the third or fourth generation of stellar material in our part of the galaxy. The first potentially habitable rocky planets formed around metal-rich stars perhaps 8 to 10 billion years ago, approximately 5 billion years after the Big Bang. So some worlds have had a multi-billion-year head start on Earth. This is the basis for the usual expectation of many older civilizations. But here is the twist. The most common stars in the universe, by a very large margin, are red dwarfs, small, cool, dim stars that burn their fuel so slowly they can live for tens to hundreds of billions of years. Our Sun, a comparatively profligate G-type star, will burn for approximately 10 billion years total. A red dwarf of typical mass will burn for 100 billion years. Some will burn for 10 trillion years, 1,000 times the current age of the universe. Crucially, red dwarfs are still forming. They will continue forming for hundreds of billions of years, and the planets that orbit them, potentially habitable planets warmed by their dim but ultra-stable light, will be around for timescales that dwarf anything our Sun-orbiting Earth can experience. Loeb and colleagues calculated that when you integrate over the full future lifetime of the universe's star formation and planetary habitability, approximately 92% of all Earth-like planets that will ever exist have not formed yet. We are in the very early phase of the cosmic era of rocky planets. The peak is not behind us, it is ahead, by billions, perhaps trillions of years. If life and intelligence track the availability of suitable planets, if there is no systematic reason to expect intelligence to arise early in the cosmic timeline rather than late, then the probability-weighted expectation is that most intelligent beings will arise in the universe's distant future, not in its present early youth. Under this framework, we are not late to a galaxy that should be full. We are extraordinarily early. We are among the first minds to arise in a universe that, by the numbers, has most of its intelligent inhabitants still to come. The silence is not the silence of a graveyard, it is the silence of a nursery in the very first hours of the morning. The implications of this, if true, are vertiginous. It means that the first civilization to survive, to navigate whatever the great filter turns out to be, whether natural or self-inflicted, inherits a cosmos that is still mostly unpopulated. It means that the choices we make, the precedents we set, the values we encode into our technology and our descendants could echo through trillions of years of subsequent cosmic history. If we are among the first, we are not merely a civilization trying to survive. We are a prototype, a proof of concept, the first experiment in whether intelligence and technology can coexist with their own long-term existence. The responsibility encoded in that possibility is almost too large to contemplate.
Let us sit with the most extreme possibility for a moment. Not the most likely, we genuinely do not know what is most likely, but the most philosophically consequential. What if we are alone? Not alone in the sense that no life exists anywhere beyond Earth. The universe is vast enough and chemistry common enough that this seems unlikely, but alone in the sense that matters most. Alone as a technological civilization. alone as a species that has developed mathematics and science and the capacity to ask questions about its own existence, alone as the only minds in the entire observable universe that know the universe exists at all. The physicist Freeman Dyson, whose work on megastructures gave us the concept of the Dyson sphere, wrote in his book Disturbing the Universe that he believed the universe was, in some sense, constructed with the emergence of mind in mind, not through any supernatural agency, but through the stunning improbability that the physical constants of the universe are precisely tuned, within extremely narrow margins, to permit the existence of complex chemistry, stable stars, and the long timescales that biological evolution requires. This fine-tuning, the subject of what philosophers call the anthropic principle, is itself a mystery that physicists have not resolved. If we are alone, if we are the only minds in the observable universe, then our existence takes on a significance that is almost impossible to articulate without sounding grandiose. We are the universe's way of knowing itself. We are the only place in 100 billion trillion stars where the cosmos has become aware of its own existence, where the nuclear fire of the Big Bang has, over 13.8 billion years, arranged itself into configurations capable of asking why. The astronomer Carl Sagan put it most beautifully, as he often did. "We are made of star stuff," he wrote. "We are a way for the cosmos to know itself." Sagan was not speaking metaphorically. The carbon in our bodies was forged in the cores of stars that died billions of years ago. The oxygen we breathe was produced in supernova explosions. We are literally the universe folded back upon itself, looking inward, asking questions. If we are the only place where this is happening, then the stakes of our survival are absolute. Not merely important, not merely significant, but absolute. Because if we disappear, if the great filter takes us, then for perhaps billions of years, the universe continues its expansion in silence, with no one to witness it, no one to ask why it exists, no one to marvel at the cold fire of the stars. This is not a comfortable thought, but it is a clarifying one. And if we are not alone, if there are others out there, hiding or silent or not yet arisen, then the question of what we do with that knowledge is equally pressing, because the universe is, on the timescales that matter, not yet decided. The outcome of this question is not written. The silence is not permanent. It is the silence of an early morning, before the world has fully woken. The Fermi Paradox is not merely a scientific puzzle. It is a moral situation. If there is a great filter ahead of us, if the history of the universe is littered with civilizations that reached our level of technological development and then failed, then understanding what destroys civilizations is the most urgent scientific and political question we face. Not climate change alone, not nuclear proliferation alone, not AI risk alone. All of these, and whatever else we have not yet identified as components of the same meta-challenge. How does a technological species survive itself? The search for extraterrestrial intelligence is, in this light, not merely satisfying curiosity, it is an investigation into our own survival. If we find a signal, if we establish contact with a civilization that has survived its own technological adolescence, the single most important question we could ask is how? What did you do that others apparently did not? What choices, what institutions, what forms of governance and cooperation and restraint allowed you to navigate the dangerous interval between the discovery of nuclear fire and the establishment of a sustainable civilization? That knowledge would be worth more than any other discovery in human history. And even if we never find a signal, even if the silence continues indefinitely, the search itself is not wasted, Because every star we survey, every frequency we monitor, every exoplanet atmosphere we analyze for biosignatures gives us more data about the distribution of life and intelligence in the cosmos. Data that eventually resolves the question of where the great filter is. Data that narrows the range of possible explanations for the silence. Data that helps us understand whether the road ahead is open or whether something terrible is waiting. The James Webb Space Telescope is reading the atmospheres of nearby exoplanets right now. The square-kilometer array, currently under construction across radio-quiet sites in South Africa and Western Australia, will be the most sensitive radio telescope in history, capable of detecting the equivalent of an airport radar at the nearest star systems. The Vera Rubin Observatory in Chile, completed in 2023, is conducting an all-sky survey that will detect any anomalous moving objects in the inner solar system, expanding our search for von Neumann probes or artificial debris. The Laser Interferometer Space Antenna, LISA, will eventually detect gravitational waves at frequencies that might reveal the presence of artificial megastructures. We are searching. We are searching with more sophistication, more sensitivity, and more breadth than at any previous point in human history. We have not found anything, but the search is young. And the most important thing, the thing that the Fermi Paradox ultimately teaches us when you stand back and look at the full sweep of the argument, is that the universe is not guaranteed to produce minds that persist. It is not predetermined. It is not certain. The emergence of intelligence is, by the evidence of the silence, either rare or fragile, perhaps both. We are here. We are asking the questions. We have the tools to search and the wisdom to interpret what we find. That is not nothing. That is perhaps everything.
We began this journey at a cafeteria table in Los Alamos in the summer of 1950, with a question so simple it fit in 5 words: where is everybody? We have walked together through the full architecture of why that question is so devastating. We have examined the mathematics of galaxy colonization, the calculations that show how rapidly a single interstellar-capable species could fill the Milky Way, and how little of the galaxy's age that would consume. We have explored the Drake equation, not as a formula that gives answers, but as a map of our ignorance, showing us precisely which unknowns determine whether the cosmos is full or empty. We have surveyed the silence itself, the 60-plus years of radio searches, the infrared surveys of 100,000 galaxies, the optical SETI campaigns, the gravitational wave observatories, the atmospheric analyses of exoplanets, and we have found, at every wavelength and every scale, nothing that compels us to conclude we are not alone. We have encountered the anomalies, the WOW signal's 72 mysterious seconds, Tabby's star's seductive dimming, Oumuamua's anomalous acceleration, the fast radio bursts that discharge more energy than our sun produces in 3 days and whose full range of origins we do not yet understand. Each of them intriguing, none of them conclusive. We have confronted the great filter, the brutal logical framework that tells us something stands between the emergence of life and the colonization of galaxies, and that the filter is either behind us, meaning we are extraordinarily rare, or ahead of us, meaning something destroys civilizations like ours, and may be waiting for us too. We have explored the full zoo of explanations, the rare Earth hypothesis, which places Earth's improbability at the center of the silence, the self-destruction hypothesis, which places the failure mode inside the nature of intelligence itself, the dark forest, with its cold strategic logic of preemptive elimination,
the post-biological transcendence, which suggests advanced intelligence becomes invisible to us because it has moved beyond the physical signatures we know how to detect. And we have ended in a place that is strange and humbling and, if you sit with it long enough, quietly magnificent. The possibility that we are early. That the universe, weighted by the long lifetimes of red dwarf stars and the trillions of years of planetary habitability still ahead, has most of its intelligent inhabitants yet to come. That we are not the latecomers to a silent, failed cosmic project, but the vanguard of something that is only beginning. Here is what we know. The universe is 13.8 billion years old, contains 2 trillion galaxies, and has distributed the ingredients for life across its entire observable volume. The number of potentially habitable worlds is measured in the hundreds of millions in our galaxy alone. The chemical precursors to biology appear wherever we look, in comets, in asteroids, in interstellar clouds, in the protoplanetary disks of forming star systems. Intelligence has arisen at least once, here, on this pale blue dot, orbiting an unremarkable star in an outer spiral arm of an ordinary barred spiral galaxy. Here is what we do not know. Whether that intelligence is unique, whether it is early or late in the cosmic story of mind, whether the silence reflects rarity or fragility or hiddenness or transcendence, whether the road ahead is open or whether something waits on it, as it has apparently waited for every other civilization the galaxy may have hosted. Here is what we feel in the face of this uncertainty, the ache of the question, the vertigo of the scale, the strange, stubborn, beautiful conviction that the silence cannot be the whole story, that somewhere, in the immensity of space and time, we are not the only ones asking. And here is what we do. We search. We build better instruments. We point them at more stars. We analyze more atmospheres. We monitor more sky. We continue, with growing rigor and growing humility, the most profound investigation our species has ever undertaken. Because the Fermi Paradox is not ultimately a question about aliens. It is a question about us, about what we are and what we might become, and whether a species capable of asking why the universe is silent is capable of surviving long enough to find out. It is a question about whether intelligence, this strange, precious, terrifyingly fragile thing that evolution produced once on one small world in one ordinary galaxy, is something the universe makes and keeps, or something it makes and loses. It is a question about time, whether we have enough of it, and whether we are spending it wisely. It is, ultimately, the oldest question that has ever been asked in any human language, dressed in the language of astrophysics and radio telescopes and exoplanet atmospheres and mathematical models of galactic colonization. Are we alone? We do not know, but we are asking. And the asking, the refusal to accept ignorance as a final answer, the insistence on building instruments to extend the reach of our senses beyond the horizon of what any previous generation of humans could see, that is itself one of the most extraordinary things about us. We have the intelligence, we have the technology, we have, for the first time in our planet's history, the ability to search. The rest is a matter of will. The universe is vast. The silence is not empty, and we have only just begun to listen.